Some of the most important types of groups that we've looked at this semester have been groups of permutations. We've seen many such groups. We've seen the full symmetric group on n elements, right? All the different ways that the numbers 1 through n can be rearranged. Those can be expressed as a group of permutations. The even transpositions, the groups of even transpositions that we call the alternating groups. Those are examples of groups of permutations. The dihedral groups, right? The symmetries of a square or of a triangle can be expressed in terms of permutation groups. In this video today, we'd like to explore just how far this theme goes, just what types of groups can be represented as groups of permutations. In other words, which groups that we've looked at are isomorphic to a group of permutations. I'd like to begin by showing you a magic trick. What I have here is an operation table for Z4, right? The numbers 0 through 3 with mod 4 arithmetic. You're familiar with this table. We've looked at it many, many times. What I'd like to do is to observe that because groups have the Sudoku property, every row in the operation table can be looked at as a rearrangement of the elements of the group. So this first one, well, it doesn't appear to rearrange them at all. It arranges them into their same order. So I could represent this, right? This first row can be thought of as the representing the function that sends 0 to 0, 1 to 1, 2 to 2, and 3 to 3, right? The identity permutation. It's represented like that usually. The second one, let's see, the second row can be viewed as the permutation that sends 0 to 1, 1 to 2, 2 to 3, and 3 to 0, right? Sends 0 to 1, 1 to 2, 2 to 3, and then 3 back to 0. The third row can be looked at as the function that sends 0 to 2, and then 2 to 0, sends 1 to 3, and then 3 to 1. And finally, the fourth row sends 0 to 3, 3 to 2, 2 to 1, and then 1 to 0. So let me draw a Cayley graph that uses these 4 permutations. I've gotten it started here. So I'm going to let this vertex represent the identity permutation, and I'm going to let a solid arrow represent multiplication by the permutation 0, 1, 2, 3. Well, let's see what happens if I do that twice. Let's see, 0, 1, 2, 3, followed by 0, 1, 2, 3. Gives me, let's see, that's going to send 0 to 1, and then 1 goes to 2, so 0 is going to go to 2, 2 to 3, but then 3 to 0, so end that cycle. 1's going to go to, let's see, first to 2, but then 2 goes to 3, and then 3 goes to 0 by this permutation, but then the next one picks 0 up and sends it to 1. So, well, I got this one, right? I got this permutation right here whenever I multiplied by that permutation by 0, 1, 2, 3. I got 0, 2, 1, 3. And let's see, if I took 0, 2, 1, 3 and followed it with 0, 1, 2, 3, I'm going to get, let's see, 1 goes to 3, then to 0. So 1 goes to, that's actually, let's do 0 first. 0 goes to 2, and then 2 goes to 3, so 0 goes to 3, 3 goes to 1, and then to 2, 2 goes to 0 and then to 1, and then 1 goes to 3 and then to 0. So I get 0, 3, 2, 1, which was our fourth permutation that we identified from the table. And then finally, if we follow 0, 3, 2, 1 with 0, 1, 2, 3, what we get is, let's see, 0 goes to 3 and then to 0. So 0 goes to 0, 1 goes to 1, 2 goes to 2, 3 goes to 3. We get the identity permutation. And so what we have is that these four permutations that were viewed as being represented by the rows of the operation table turned out to form a group. In fact, turned out to form a group. You'll recognize this Cayley graph as a Z4, which is exactly the group we started with. Magical. Let's try it again. Let's try it with our other 4-element group, the one that for which every element is its own inverse. Let's see, what do we have here? So this is, again, the first row can be viewed as representing the identity permutation. So I think I'm going to call that, let's write E this time for that. And then let's see the second one. So E's going to A's going to E, B goes to C, and C goes to B. And, you know, I think I'm going to, since this is coming from row A, I think I'm going to call this permutation A. I'm using the symbol pi to denote permutation. That's often done. I'll do the same for the identity up here. I'll call this pi sub E. I wonder what pi sub B is going to be. So let's see. So that's going to send E to B. It's going to send B to E. It's going to send A to C and C to A. And then from the fourth row, the row headed by C, we're looking at the permutation that sends E to C, and then C is going to go to E. A is going to go to B and B to A. So we have these four permutations, and if we try to plot those on a Cayley graph, let's see, I've put a couple of them down here. So pi sub E, I'm going to let that be identified by this vertex, pi sub A over here, and I think it's pretty clear that this is going to be its own inverse. Pi sub A is its own inverse. In fact, all of these are their own inverses. You can check that if you like. So I'm going to use a solid line there to indicate a bidirectional arrow. Let's label this as pi sub B. So what is that again? That's EB AC. And if I follow that from the identity, I'm going to get a bidirectional arrow there. Let's see what happens if I start with EB AC and do a solid arrow to, let's see, so that solid arrow represents E, A, B, C. So let's see, that's going to send E to B and then to C. It's going to send C to A and then to E. A is going to go to C and then to B, and then B is going to go to A, which is in fact the one I had not written down yet. That's coming from the fourth row of our table. So that's pi C. Right, and I'll let you check for yourself that if you follow pi C with pi B, pi A is what you get. And so what we wind up with is, well, this is isomorphic to, we've looked at this in a couple of different guises. One of them, Z2 cross Z2. Right? But that's exactly isomorphic to the group that the table was describing that we started with. So this is isomorphic to a group of permutations as well. This is pretty exciting. It's starting to look like we might be able to use this technique on just about any group. I mean, there's a natural question here. Can every group be represented as a group that's made up of the permutations that are suggested by this operation table? Well, first of all, the quick answer is going to be no, simply because not every group can be represented with an operation table. Imagine the real numbers under addition, for example. You would never be able to draw such a table. However, I think that the process that we used up here will be able to be used more generally, even with infinite groups. Let's look back up here at pi sub A again. Where did these elements come from? How did I know that E was going to A, that A was going to E, that B was going to C, that C was going to B? I mean, yes, I just looked at where the positions of those elements were in the row, but could I not also have noted that pi sub A is going to send, well, let's see, where's it sending B, for example? Well, it's sending B to C, but I could also represent C as A times B. I'm going to use an asterisk for the operation here. So, right, pi sub A of B could be thought of as A times B. Sticking with pi sub A again, pi sub A of C, for example, well, let's see. That's in the position in the table that I'm getting A times C from. Right? B is A times C. Right? That's B. Right? A times B from before that was C, and so on. So it kind of looks like, in fact, it looks exactly like I could define this permutation very generally. What's it going to do to X? It's going to send it to A times X. And I don't need an operation table in order to write that. I could use this idea even with infinite groups. And that's exactly what I'm going to do. Let's let G be a group, any group at all. And I want to define a function from G to G. Right? I'm going to pick an element out of G, first of all. And I'm going to identify a permutation that's associated with that element. I'm going to call it pi sub A. And I'm going to define it, well, I think you can probably guess, just like I did over here. I'm going to define pi sub A by saying it's going to send X to the element I get whenever I left multiply A by X. I'd like to show that such a function, it's certainly a function, right? It's certainly a function because I'm in a group, so I can always multiply two elements in that group and get another element in the group, so it's certainly a function. is it 1 to 1? I want to show it's a bijection. So let's begin by showing it's 1 to 1. And how do I do that? Well, the standard way of showing that a function is 1 to 1 is to pick two elements out of your set, out of G in this case, for which the function sends those elements to the same element in the codomain, and then prove that this implies x equals y. That's the standard technique. That's what we're going to do. So we're assuming that pi a of x and pi a of y are the same. Well, by definition of our function, that means a times x and a times y are the same. Right? Again, my goal is to show that x and y are identical. There's a natural thing to do now, right? I can multiply both sides by the inverse of a. Remember, G is a group, so every element has an inverse. So A has an inverse. But then by associativity, I can then get that the identity element times x is the identity element times y, which tells me that x and y are in fact the same. Reading this backwards, it says that if I have two different elements in G, they're going to go to two different elements in G, right? This is a 1-to-1 function. Is it onto? Well, it is. Let's show it. So the standard way of showing that a function is onto is by picking something out of the codomain and showing that there's something in the range which maps to it. So I'm going to pick something out of the codomain. Of course, range or domain and codomain are the same in this case, but here I'm thinking of B is coming out of the codomain. And let's see. I know several things here. I know that, well, G is a group, A is in G. And since G is a group, A inverse is going to be in G. And so A inverse times B is going to be in G. So what? Well, that element, if I apply pi sub A to that element, what am I going to get, right? What's pi sub A of A inverse B going to be? Well, pi sub A of A inverse B, by definition of the way we're defining the function, that's going to be A times A inverse B. Again, by associativity, that gives us that the identity times B is the result, and that's equal to B. So I picked something out of my codomain, and I found something, here it is, I found something in my domain that maps to B. So B's onto, right? So the first part said pi sub A is 1-to-1. Second part said pi sub A is onto. That tells me that every one of these guys is going to be a permutation. Well, we're well on our way here because keep in mind what our goal is. We're trying to show that that a generic group can be expressed as a group of permutations. Well, at least now for each element of G, we have a permutation that we can at least identify with it. Let's see what we can do with that. So each pi sub A, for each A and G, pi sub A is a permutation, right? So that says that if G is a bunch of elements like this, then these functions, pi sub A, pi sub B, pi sub C, each of those are permutations, so that's a subset of the group of all permutations of G. Remember, this is the notation that we used to indicate the set of all permutations of G, which this is a known group, right? This is a group with respect to composition. So that I don't have to keep on writing this down, let's call this G prime, just to give it another name. So everything in G prime is a permutation of G. What I'd like to know is whether or not this subset is actually a subgroup. Now, noticing that it was a subset of this known group is going to simplify our work a good bit. Do you remember how we show that a subset is a subgroup? How we test it? You may recall it has to be closed with respect to the operation, which in this case is composition. We're working with permutations here. So we'd like to show that the set of, if I take any two of these permutations and compose them together, that I get another one of these permutations. That would show closure with respect to the operation of composition. And then I also have to show that it's closed with respect to inverses, right? Every permutation has an inverse. So I need to show that if I pick a permutation out of here, that its inverse permutation is also one of these guys. So I need to show those two things. So let's begin by showing that this set G prime is closed with respect to the operation of composition. All right, so how do I do that? I pick two elements out of G prime, call them pi sub A and pi sub B. Of course, that means that A and B are in G. That's where these pi's came from. And we want to show that their composition is also in G prime. The composition is also one of these. Well, let's pick something out of G and notice that if I compose those two functions together and apply x to it, then let's see, I get, by definition of composition, I'm going to have pi sub A of pi sub B of x. By definition of pi sub B of x, well, let's see, pi sub B of x is B times x. So this is pi sub A of B times x. But then again, by definition of pi sub A, that's going to be A times B times x. But we're in a group. The operation's associative. So I can write this as A times B times x. But isn't that exactly, keep in mind, right? A times B is a member of G, right? A times B is in G. And so I can recognize that this element of G times x can be written as pi sub that element of G of x, right? This is one of the things in G prime. So since this function does what this function does to each element of x, and this function is in G prime, that must mean that this function is in G prime as well. And so what we have is that G prime is in fact closed. If I compose any two members of G prime, I get another member of G prime. It's closed with respect to composition. Right now, I'd like to show that it's closed with respect to inverses. This is actually a little bit easier, right? If I take anything out of G prime, then well, let's see. That means that A is going to be in G, so G is a group, so A inverse is in G also. So I have a pi A inverse. But if I take any x out of G and apply pi A of pi A inverse to x, what I get is, let's see, by definition of composition, that's going to be pi of A, pi sub A of pi sub A inverse of x. And then by definition of pi sub A inverse, I can write A inverse times x for the image of x under pi A inverse. And then by the definition of pi sub A, that can be written this way. But this, after using associativity, is just x. Well, what that shows me is that whenever I compose pi A with pi A inverse, I get a function that sends x to itself. Well, that's the identity map. That shows me that this composition is the identity map, which must mean that pi sub A inverse is the inverse function of pi sub A. A similar argument would show me that I could go in reverse, that pi A inverse of pi A of x is also x. And so with that, that tells me that G prime is closed under inverses, right? If I take any element out of here, say pi sub c, well, pi sub c inverse is also in here, and pi sub c inverse turns out to be the inverse of pi sub c. So sure enough, this set is closed. Under the operation, it's closed under inverses, and since it was a subset of this group S sub g, these two facts are enough to tell me that G prime is in fact a group of permutations. It's a subgroup of S of G. Everything in S sub G is a permutation, so G prime is a group of permutations. It's not all the permutations on G, but it's a subgroup of the group of all permutations on G. Well, we're making a lot of progress here. All right, we've shown that for every element of G, we can associate it with a permutation of G. And now we've shown that the collection of all of those permutations is in fact a group. That's exciting. What would we like now? Well, now we have this group of permutations that's a reasonable candidate for a group of permutations that just might be isomorphic to G itself. After all, let's go back and look at what we had done earlier with Z2 cross Z2, right? This was our group G. For each element of G, we identified a permutation, right? The permutations were defined this way. We proved that what we have really is a permutation, right? So pi sub a really is a permutation. And now what we'd like to do is show that this collection of permutations is in fact, just like we did here, is isomorphic to our original group. Our original group had this Cayley graph, and the group of permutations that we've just identified also has this Cayley graph. So this group is isomorphic to a group of permutations. That's the only thing we have left to do now, is to show that in general, that this group of permutations is isomorphic to the group G that we began with. How do we do that? What does that mean? Well, we're going to use our definition of what it means for two groups to be isomorphic, our new definition, not the one that involves Cayley graphs, but the one that involves isomorphisms. We need to find an isomorphism between the group G and the group of permutations that we're associating with G. And there's a very natural function which is likely to do the job. Right? Let's define a function from G to G prime by sending each member of G, well, to the permutation that we're associating with G. If this is going to be an isomorphism, that means it has to be a bijection and it has to preserve the operation. So let's begin by showing that F is in fact one-to-one. How do we do that? Well, just like we did before, right? We're going to pick two things out of G for which F of A and F of B are the same, and we're going to show that that means that A and B have to be the same. All right, well, let's see. If F of A and F of B are the same, then by definition, let's see, what's F of A? Well, F of A is the permutation pi sub A. F of B is the permutation pi sub B. So if F of A is equal to F of B, then that says pi A is equal to pi B, which means these two functions are going to do the same thing to every member of G. So if I pick a member of G, pi A of X is going to have to be pi A of B. But by definition of these permutations, that means A times X is B times X. But then I can multiply both sides, right? Remember what my goal is. My goal is to show that A and B are the same. Well, X is in a group, so X has an inverse element. Let's multiply both sides on the right by X inverse. And after using a little associativity, we can conclude that A and B are the same. So this does, in fact, show that this function that we're defining between G and G prime is one-to-one. Is it onto? This is particularly simple, right? Again, you show something's onto by picking something out of your codomain and proving that there is something in your domain that maps to it. But if pi sub A is in the codomain, well, that means that A is an element of G. But by definition of our function f of A is pi sub A. So we're done, right? F is in fact onto. So F is one-to-one, F is onto, F is a bijection. Let's just note that. So F is a bijection. If it's a bijection that preserves the operation, then we've got it. That's the only thing we need. We need to finish showing that F is an isomorphism. So let's show that F preserves the operation on G. What's the operation on G? Well, I'm going to use star to denote the operation on G. And so if I pick two things out of G and I multiply them together, where's it going to send F? Or where's F going to send that element? Well, this notation looks a little odd, but keep in mind that F is sending members of G to a function, right? To what we've shown, in fact, is a bijection. So F of A star B is a bijection. It's a function. So it makes sense to talk about what this function does to X. Well, the function it sends it to, F sends each A to pi sub A. It sends pi sub B to, or sends B to pi sub B. It's going to send A star B to pi sub A star B. And so I have that this function applied to X is equal to this. But by definition of how I've defined my pi's, this is going to be A star B times X. Yes? And by associativity, that's A star B star X. So this is exactly what pi A does to B star X. And B star X is exactly what pi sub B does to X. And so what I've got is the composition of pi A and pi B applied to X. Right? So it turns out that this function right here is exactly this function right here. But what is pi sub A? Isn't that what F sends A to? And isn't pi sub B what F sends B to? It is. Pi sub A is exactly F of A. Right? It's the permutation that F sends A to. And I'm composing that with F of B. So there I go. If I multiply in G first and then look at the image, I get the same thing as if I look at the images first and then multiply in G prime. So F does preserve the operation. So it's a bijection, and F is operation preserving. Right, and so as a conclusion, we have that F is in fact an isomorphism. That's exactly what we were going after. That's the grand finale, isn't it? Right? Because what it says is that this group that we began with is in fact isomorphic to a group of permutations. So every group is isomorphic to a group of permutations. This is a very celebrated result. It's called Cayley's theorem. Cayley's theorem after the British mathematician Arthur Cayley. He proved this in, I believe, 1854. Actually, I have a little picture of him I'd like to share with you. This is the man. This is the man who proved the result that we just looked at. And it's a very, very important result, in fact. Why? Well, what this tells me is that the study of all groups can be reduced to the study of simply permutation groups. If we know everything there is to know about permutation groups, and we don't, but everything that we do know about permutation groups, we know about all groups, because all we have to do now is, if we want to answer a question about a particular group, we can find the permutation group, a permutation group that's isomorphic to the group in question, answer the question in the setting of permutation groups, and then translate that answer back into the setting that we're working in. So homework, a couple of homework problems I'd like you to do. So what I want you to do is to take the groups that are represented by these Cayley graphs down here, and I want you to identify permutation groups that are isomorphic to them, right? I'm going to do that similar to the way we looked at the two groups at the beginning of this video, right? Z4 and Z2 cross Z2. Then I want you to use the permutations that you develop to relabel these graphs, right? So that we can see that they really do give us groups of permutations that are isomorphic to the groups that are given here. And then I'd like you to verify your work by showing that the products of at least 3 pairs of permutations produce what your graphs suggest. That's a bit of a mouthful. Let me get you started with this group over here. So let's see, with this group over here, I'm thinking of 1 as representing the identity element, and so arrow is going to be multiplied by 2, not in any modular sense, but this is just going to mean multiplied by this element that I'm labeling as 2. And so multiply twice by 2, I get 3. Multiply 3 times by 2, I get 4. So, right, 3 arrows gives me 4. So that'll allow me to represent, or to build a group table. So, for example, if I wanted to do 3, well, let's see, 1 is my identity element, so 3 times 1 is 3. 3 times 2, well, again, 2 is represented by just a straight arrow, so 3 times 2 is going to be 3 followed by a straight arrow, gives me 4. 3 times 3, let's see, 3 is represented by 2 arrows, so 3 times 3 is going to be 3 followed by 2 arrows, that gives me 1. 3 times 4 is going to be starting at 3, and then, let's see, 4 is 3 arrows, so starting at 3 and doing 3 arrows gives me 2, and so on, right? So we can build row 3 in this way. Similarly, I can build row 5, I can build row 7. And then once I have those, I can identify, of course, you're going to do this for all the rows. going to identify what permutation associated with the element 3 is. Well, let's see. That sends 1 to 3, 3 to 1, sends 2 to 4, 4 to 2, sends 5 to 7, 7 to 5, and it sends 6 to 8 and 8 to 6, right? And similarly, we can build, say, pi 5 and pi 7. You can double check to make sure that you get the same answers I got there, and then go ahead and relabel the graph. So in place of 3, I have pi 3. In place of 5, I have pi sub 5. In place of 7, I have pi sub 7. Right, so you'll relabel the graph, and then I want you to check. So I have one pair here. Pi 3 composed with pi 5 gives me pi 7. So I want to start with pi 5, follow it with pi 3, and pi 3 I get to with 2 arrows. So if I start at pi 5 and do 2 arrows, I get pi 7, which is in fact what I get whenever I multiply those permutations together. Right, so do this, fill out the table. Here's one pair, find 2 more pairs to check, make sure that they agree with the Cayley graph, and then do that for Z3 cross Z2 as well. And I will do that also, and we'll post the answers, and we can check our homework next time. And that's the celebrated theorem of Cayley, of Arthur Cayley, from 1854. Fascinating theorem. Tells us that no matter what group we're working with, we can identify it with a group of permutations. Hope you enjoyed this. It put everything together pretty much that we've been talking about for most of the semester, all into one theorem. I look forward to seeing you next time. Until then, stay well. Take care.